Hello everyone. It is known that the limit as x goes to 0 of sine of x over x is equal to 1. This is a formula that we learn when we start doing limits of trigonometric functions. But the question is, what is the proof for that? And that's what I'm going to show you in this video. I'm going to prove it in two different ways. Let us start with the first method. The first proof is based on geometry. Let us consider a circle of center O and radius 1. We assume that the central angle AOM is equal to x. Then we draw a tangent line AC at A. Let us now find the area of the triangle MOA, the area of the sector MOA, and that's the region in blue and orange, and the area of the triangle COA. Before that, it is obvious that the area of triangle MOA is less than the area of the sector MOA, which is also less than the area of the triangle COA. Alright, we start with the area of triangle MOA, and that's the base OA times the height, which I'm going to call MB, divided by 2. OA is equal to 1. Why? Because it's a radius of the circle. What about MB? Since MOB is a right triangle at B, we can apply right triangle trigonometry, and we have sine of x is equal to the opposite side, that is MB, over the hypotenuse, that's OM, which means MB is equal to OM times sine x. But again, OM is a radius, so it's equal to 1. Therefore, MB becomes sine of x. And we end up with sine of x over 2. What about the area of the sector MOA? It is equal to the central angle, which is x divided by 2 pi, multiplied by the area of the entire circle, that's pi r squared, and this is a formula, but the radius is equal to 1, so we end up with x over 2. What about the area of triangle COA? Since COA is right at A, we can also apply right triangle trigonometry. We have tan of x is equal to the opposite side, that is CA, over the adjacent side, that is OA, which is equal to 1 because it's a radius, and we end up with CA equal to tan of x, and we get the area of the triangle COA is equal to the tan of x over 2. We now come back to this inequality, and we end up with the following relation. Let us multiply everything by 2. We get this. Before we proceed, we have to keep in mind that x is between 0 and pi over 2. So x is greater than 0. When we say x approaches 0, this means x is either approaching 0 from the right or from the left, but it's never equal to 0. So here we are assuming that x is positive. What about x negative? I will talk about it after we finish this. So since x cannot be equal to 0, this means that sine of x is never equal to 0 in this interval. So we can safely divide the entire inequality by sine of x. And this is what we get. Let us apply the reciprocal. The inequality signs are flipped, or we simply write it like that. Now what if we replace x by negative x? I mean, what if the variable we are dealing with is negative? Well, sine of minus x over negative x is equal to sine of x over x, and the cosine of negative x is equal to cosine of x. This means that the inequality also holds for x less than 0. We know that cosine of x approaches 1 as x approaches 0. And 1 of course approaches 1 as x approaches 0. This means, applying the squeeze theorem, sine of x over x also approaches 1 as x approaches 0. And we have finished the first proof. The second proof is based on using the Maclaurin series of sine of x, and it's this formula. X minus x to the power of 3 over 3 factorial plus x to the 5 over 5 factorial, etc. If we divide both sides by x, we get the following expression. And then, this means that the limit of sine of x over x, as x goes to 0, is equal to the limit of this expression as x goes to 0 as well, which is obviously equal to 1. And this is the second proof. That's it for today. Thank you for watching, and see you in the next video.